Right. Good morning, everybody. Thank you for turning up to listen to my talk. So it's on data privacy, and I will suggest an approach and also discuss a case study which is on in cluster analysis. Right. So the talk will cover this point: issues with big data, privacy and confidentiality. What we mean by that. A new approach, which is privacy by proxy, and complexity theory and NP-completeness. I hope I will not worry you too much about some technical words there. It may not be your area, but I will try to explain it. And then I give my case studies and report some results. Right, so what are the issues with big data? Big data requires storage, maintenance, transmission, and analysis. And it's costly to store, to maintain, transmit, and analyze. We know all that. And the bigger the data set, the more costly it is to do all these things. Sharing it may lead to replicating the data. So if you want to give someone, your data set to work on, you replicate it because you don't want to give them your only copy, just in case they lose it. So more storage. Replication copying leads to potentially compromising the privacy and confidentiality of the data. Once you give it away, show it to a third party, you compromise the privacy of the data. Now, you could say, I'm not giving you a copy, so you grant people access, but if you grant access to people to your systems, you may even compromise the security of the whole organization and not just the privacy of that data, particular data set. So there are problems with big data. So potential loss of privacy is the biggest issue inherent to big data. That is my opinion. I think that's really the biggest problem we have today. Everything else, so far, we can deal with using brute force, fast computers, a lot of storage, and so on, or affordable storage and so on. Privacy is still, in my view, a very, very big issue. What is privacy? It's the non-disclosure of valuable information to a third party. Here, we should be a little bit clearer on terminology and meanings. Data and information are not exactly the same. They overlap. And so it's really information, but because information comes from the data, so we're talking about the data privacy. Data privacy is compromised when a third party is involved. So why do we need a third party to be involved? Well, because we cannot store it ourselves. We cannot store the data ourselves. We do not have in-house capability to analyze it. And so there are other reasons. So it is unavoidable by virtue of what I have said just before, by virtue of it being a big data set. If it is small, maybe you could do things yourself, especially storage. If it's big, there are all sorts of issues. So data protection and confidentiality are really necessary. So what are the current approaches? How do you protect privacy and confidentiality today? Well, the administrative one is the most common. You sign a binding contract against disclosure. You just tell your third party, I will show you the data. You sign on the dotted lines that you are not going to show it to anybody. The problem is that people move companies, and then, once they move, you have signed the deal with the company, not with the individual, and therefore, the privacy, the confidentiality is potentially compromised. Technical. So the technical approach, the one which I'm concerned with, is this. So at the moment, you encode the data encoding and homomorphic encryption. So you pick up your data set D, and then you turn it or you encrypt it into D dash, and then you analyze. So you give D dash to your third party, your contractor, or your analyst, and then you show them D dash. Then they analyze D dash, and then they give you the results, so the results of the analysis, and then you interpret that back to fit the original data. That's really the way people are trying to do it, okay, at the moment. So there are other mathematical devices which are they are low, if you like, replacement of data, which is similar to the previous one, and this is known as fully or homomorphic encryption. So this is finding some functions that will pick up your data set and turn it into another one, and then work on that. So this is what the kind of the mathematicians are trying to do today. Now, the shortcomings with that is that this homomorphic encryption and other maths devices do not work for large data sets. They are okay when, you know, we want to illustrate some cases, etc., but on really practical data sets, they do not work. Early encryption, things which are common today and known for a few years, schemes, they support only single operations. So once you transform your data set D into D dash, on D dash, you cannot really do, you know, apply too many functions. You cannot, for instance, apply, you know, log function or do complex algebra. You can pretty much do only add and multiply, you know, really very basic operations. If you try to do anything else, you cannot come back to the original data set and interpret the results. Same thing with the FHE schemes, and this support multiple operations, and technically they should allow to do, you know, inner products, which means that you can do covariance computation and analysis and regression, but this is, you know, it's really early days. There are very, very few results, and the results are only on small data sets. So these are the shortcomings I am aware of. Because of these shortcomings, so I thought I'll see if I can suggest something in place a little bit better. So instead of doing what I have said, change D into D dash, analyze D dash, interpret results on D, we consider now the problem. What is the problem you are facing, you know? You want to specify that problem, the analytics problem that you have. And so we pick up the problem itself. So it's P, and we turn it into P dash. Okay? So we transform P into P dash with some transformation T. You have to find this transformation, of course. Then you solve P dash to obtain solution X dash. And then you pick up X dash. You apply to it the inverse transformation T. So T minus 1 X dash should give you X. And X is the solution to your problem P. So this is what really the idea is. So when you give me a problem to deal with, to analyze it, let's say you ask me to do some, you know, machine learning on it, I am not going to look at, say, this is the data, and I want, you know, to transform the data and apply some machine learning tool to it. I will change the machine learning. I say, well, you want me to do some machine learning? I will do something else. Can I do that? That's the idea, okay? It's a little bit counterintuitive, but the next slide will tell you that it is not. So what are the questions? We want to know what is P dash. So once we have decided on what we want to do, so we know our problem, P, what is P dash? And then, of course, what is T? How do you get P dash from P? You need a T. That's where this beast comes into play, and that is complexity theory. Now, there's nothing new here. I'm not really bringing anything new in terms of technique. What I'm bringing you is putting these two things together. It's like it's kind of sideways thinking, okay? It's lateral thinking. So what is complexity theory? Well, it characterizes computational problems in terms of their difficulty with respect to each other and the solution approaches or algorithms available to their solution. So complexity theory just wants to tell, you know, to say, if given a problem, how hard is it to solve computationally? So worst case analysis uses two broad classes of algorithms for their characterization. There are those that run in polynomial time and those that run in exponential time. Exponential time means expensive, difficult. Polynomial time means nice, does not take too long to solve. Even when you change your data, the size of your data, the change in execution time will only change in polynomial, you know, in a polynomial form rather than a high-cup in exponential form, okay? Now, there are two main classes of complexity, and these are the P class. The P class contains problems which are, you know, considered to be easy. That means there are polynomial time algorithms, so algorithms that run in polynomial time that can solve these problems, and the NP class, which are the problems for which there are problems that run in polynomial time, but only non-deterministically. Okay, so it's in a probabilistic sense. And the NP-complete class, which is the third class really we are concerned with, is all decision versions of problems for which there is no known algorithm that runs deterministically in polynomial time. Okay, so this, we cannot put them at the moment in the P class, they are difficult. And equivalently, there are those for which only algorithms that run deterministically in exponential time are known. That means if you want to run them, to solve them, then we only know algorithms which run in exponential time. These are the NP-complete problems. These are pretty much the hard problems we deal with today. Okay, so if you want to do optimization, nonlinear optimization, clustering, data mining, classification, all these are difficult. We don't know how to deal with them deterministically in polynomial time. Okay? Now, the important thing here, the most important thing here, is that if any one of these problems can be solved in polynomial time, then so can all the others. That's really the beauty of this complexity theory thing. It says that NP-complete problems are very difficult to solve. We don't know how to solve them efficiently. But, and there are a lot of them, I will show you in a minute, but if you can solve one of them well, or fast, or in polynomial time, so can you solve all the others. That's really the thing. It just says that, in fact, all these problems are really the same problem under different guises. That's difficult to accept. You have to read a little bit more on complexity theory to accept it, but trust me, this is not new technology. This is 60s, 70s, 80s, technology. And so, of course, this is unlikely. We cannot solve these problems, fast, because otherwise it would be that P is equal to NP, which is not believed. People believe that P is really different from NP. The two classes, P and NP classes, are different. Okay, so now I said that we need to find P dash for your problem P. P dash, can be picked up from the NP-complete class, which is really vast. And so all these problems are NP-complete. Subset sum, set covering, knapsack, traveling salesman problem, the Chinese postman, clustering. I highlighted clustering here because this is the one that data analysts really do, or deal with, or need to deal with. And this is the one I'm going to illustrate this idea on. Now, this is a tree that shows this NP-complete class. As you can see, it is a graph, and this is a connected graph. There is no single node which is on its own. They are all connected. What this says is that there is a transformation which goes from one node to the other. So an edge just says that, in fact, there is a transformation. So if one of these nodes is your problem P, the one which is it connected to is your P dash. So you pick and choose. In fact, this graph should be complete in the sense that you should connect all the others one to each other. You can go from any node to any other. Why these edges are not shown here? It's because in the literature, people have just worked on one to show that your problem is NP-complete and add it to the class. But if you want to find a non-existing edge there to establish it, you have to find T, and it's not easy. The good thing is, mathematically speaking, this T, or this edge, exists, and it can be computed in polynomial time. Because otherwise, if you transform, the transformation is as hard as the original problem, so what's the point? So the theory says the transformation is cheap to compute. So that's the beauty of it. So if you give me a problem P, which is in data analytics, let's say here is clustering, I have got all these problems to choose from. Any one of them will do. Okay, so I've got plenty to do. So there we go. Here is a case maybe to illustrate. A hospital has a large medical data set that needs analysis. Grouping together patients according to some criteria is needed. The hospital has no in-house analytics capability. Third party is called upon to do the analysis, but the data needs protection. This is the situation. Solution: clustering problem P is NP-complete. I know that. There is literature which says clustering is NP-complete. That's known. Convert into TSP. as problem P dash. So I decide that because TSP, the traveling salesman problem, have you heard of the traveling salesman problem? It's probably the most sexy, the most known, the easiest to state problems in combinatorial optimization. Everyone knows the TSP. It's easy to state, yet very, very hard to solve. And so, because they are both clustering and TSP are both in this NP-complete class, I choose to change my clustering problem into TSP. Okay, so if once I have transformed P, my clustering problem, clustering the medical data, to a third party, I will transform this clustering problem into a TSP, and I will show the third party a TSP problem. So can you please help me to solve, find the shortest tour for my traveling salesman, in this set. How would I do that? See here. So the clustering is against TSP. The objects to be clustered are turned into cities. The dissimilarities between the objects are the distances between the cities, and the objective is to group similar objects in the same clusters and non-similar ones in different clusters. The objective here is to minimize the tour length, guaranteeing visiting the group of closed cities consecutively. So that's how we do it. So 2 factors guarantee privacy and confidentiality of the data set. The first one is change of context from a medical problem to a logistics one. So when I show you my problem, which is initially it is clustering. I'll show you TSP. So this is a logistics problem. So you will never, as a third party, if you want to snoop and you want to check what data I have, you will never guess. Say I work in a hospital. I'm not going to give it to you myself. I could pass it on to somebody else who will give it to you as a TSP. So you can protect the privacy of the data quite fully. Transformation of a database of names, personal details, and clinical parameters into a distance matrix recording the distances separating cities. So here, I have to transform also all the data into a distance matrix. And so that's what it is. And so these 2 factors are the ones which guarantee confidentiality. How much time have I got? 4 to 5 minutes, right? No medical data. I don't have medical data to play with, so I chose to play with some data which is available online, and that is clustering EU countries and Turkey according to criteria known as the Copenhagen criteria, and these criteria span political, economic, and acceptance of the community acquis aspect of the EU organization. So this is a nice problem in the sense that we want to know whether Turkey fits or not using clustering, okay, just to bypass the political approach. This is a statistical approach, okay? So what I do is I pick up the data from Eurostat and Turkstats repositories, and then I normalize the data, and this is what I get. I get a table of normalized scores, and this table could be, if it was medical, it would be exactly the same. You will have, for instance, population would be the population of patients, and then the marriages could be something else, and so on. So this is a table, and it's normalized. The reason why you get minus 47 for population of Belgium here, the negative thing is because when you normalize this formula here, this expression here, xij minus the mean is bigger than the population of Belgium. Obviously, that's negative, okay? And the denominator is positive, so you get a negative value. So don't worry about the negative values. Those are generated by the normalization process. So this is my data. Still, this is the data I have got. Now this is for clustering. I turn that into a distance matrix. This is what I get. This is my distance matrix. My distance matrix is symmetric because I assume that my TSP is symmetric. So you go from A to B, the distance is the same as going from B to A. That's why you get 30 for Bulgaria there. And in the middle, you've got 1,000 there. That's a big distance because in the TSP, you don't go from the same city to itself. You don't do loops like that. And therefore, to avoid it, you put the distance between the city and itself huge. You could infinity, but here it's 1,000. It's big enough. So my algorithm will never choose this value to include in the tour. Okay, this is just a trick really used in the TSP. There we go. So the results are here. It is. So then I solve my problem now. This one here, I solve it using optimization problems. Some I use the genetic algorithm, I use simulate annealing, anything. And then once I get my results, I'm not showing you all the steps because I don't have time. And then I go back and cluster. Okay, from the tours, I get this clusters here. As you can see, with 3 clusters, I have got Turkey here with a number of people, a number of countries, including the UK, France, and Germany. But Slovenia, funny enough, does not fit. And here's for seven clusters, and Turkey is still with France, Spain, and Italy, while Germany does not fit, Luxembourg does not fit, etc. Okay, so to conclude, loss of privacy is a big issue. Current techniques, for data privacy are well below expectation. Our idea is safe and relies on proven technology. As I said, I have not all the technology, all the stuff I explained, it exists already. It can be really extended to other core problems, such as supervised learning, classification, regression analysis can be done, data mining, and so on. All these are NP-complete problems, and therefore we can do them. Thank you very much.
Thank you very much. I'll quickly introduce myself. I'm Zeebo Hanno. I'm working as a research officer in EIS Lab. So I'll be talking about how we analyze visual big data using computer vision applications. So in recent years, we have seen that big data has grown. There's so much amount of data, computed data, and this can be actually attributed to popularity of internet. So from social media, popular social media platforms, or online retailing websites, or even Netflix. So all we see is that in a single minute on internet, we are generating around 64,000 gigabytes. So in 2016, Cisco did this study where it found that 73% of the data generated online is actually visual, and which is going to grow to 82% till 2021. And if I would like to quote from the study, it said that for a single person to watch the entire videos, it will take 5 million years. That's why we call visual data as the dark matter of internet, or the undiscovered area. So if this is the visual data online, well, let's look at the data which is generated offline. So all the research, whether it's in the medical sciences, or even the underground water, or the space research, the main explanation is actually through images. And apart from that, there was a study which said that in soon we will have more number of smartphone as compared to people. So if we are having a lot of visual data online as well as offline, it's not possible for us to sit and actually analyze them. So we need to automate this process. So if we look at the picture on the left-hand side, we can see that it's actually snowing. But if I give this picture to the computer, it will just be mere numbers, like a matrix of numbers. So it's going to be a very difficult task for us to for a computer to understand what the picture is saying. So if I have to actually define computer vision, I can define it using 3 R's, which are recognition, reorganization, and reconstruction. So in the recognition, what do computer vision scientists do? They actually assign semantic labels to each object in the picture. So as you can see, it will try to identify the cow, and then try to see which animal it is, so it's cow. Then again, at the same time, it will try to see its boat, and then a person. And if we see in reorganization, what we do is we try to segment that image into certain objects, or into set of pixels where each set is actually indicating an object. And in case of reconstruction, since images are just 2D numbers, we are losing depth. So we try to recover the depth as well as the other properties like reflectance property. So let's do a quick task. Now, if we look at this if we look at these array of pictures, we can easily see it's a cat. So let's start from left-hand side. So the top left-hand side, the 3 pictures, they all are cat. But we see that the camera position has changed. But still, we are able to recognize it's a cat. So the last picture on the right-hand side, and just down, we can still say it's a cat, but even though those pictures have been taken in day and the other one has been taken in night. And then cat as an animal is known to deform itself. So if we look at the middle pictures, we can still say it's a cat, even though the shape of the object is changing. But at the same time, if we look at these two pictures, these two pictures, it's occluded, or cat is hiding behind, or even in the last case, we are just able to see the tail, but still we can say it's a cat. Now, then there are many cats, right? But still we know they're cats, even though they're hiding behind each other. Now, cats are, in these two pictures, if you can see that the cats have this habit of actually trying to match the background, like, not having much contrast, then still we are able to see it's a cat. So the kind of marvel we have with the computation power, can computer actually match that? So these are the major challenges which we will face when we try to understand visual data. One is called viewpoint invariant. The other one is the certain illumination changes, occlusion, or deformation, or background clutter, or intra-class variation. So, but if we have to actually get inspired by how humans recognize or how humans try to understand images, so if we had this picture of a cat, how we will recognize it's a cat? So we associate certain features with it. So we know as cats have certain parts. That's why when even a single tail was visible, we could say it was an image of a cat. If I could go back to this slide. So we just knew even with a part of it that this is a cat. So we associate certain features with it. So like, for instance, ear, tail, eyes, a certain shape of the body, or for instance, like it will just have 2 ears. So if we see an object with 3 ears, we can say it's not a cat. Now, so we try to take this as an inspiration for the work in computer vision. Now, suppose we have this picture of the same mountain, but taken from different viewpoint. We try to detect those points which will be repeatable. When I mean repeatable, that even when the image will undergo various transformations, I can still detect it. So there are series or arrays of feature detector which have been inspired by various techniques, and then we try to match them if we can see which one of them is there. So this is commonly used in a technique called panorama. Just to give you an example now, feature detection is also used in, again, panorama generation, but this is just step-by-step how we try to match features and get a proper image. Now, the pipeline in feature detection can be divided into 3 parts. So it's detection, where we try to identify those points which are very stable and repeatable in case the image is undergoing those challenges which I mentioned previously. Then trying to describe it. So with description, I mean not just the point, but trying to keep in mind what the neighborhood is actually saying, and then trying to match it when a new image comes. So, but what we decided to do is step back. So there are like seas of feature detector, and each one of them in the paper will claim that it is better than the other. So, but so computer vision has become very popular, and as a person who's not from a technical background, or even is just trying to use it, so which one should we choose? So what we did was we published this work in 2016 in a remote sensing journal. So we decided to actually make a statistical framework where a person can actually take certain data set and try to choose any feature detectors they want, and then try to match its performance and say that this one will work in this circumstances or this one will work in the other circumstances. So the statistical framework is actually divided into 2 phases. In the first phase, what we did was we actually wanted to know what was the upper bound performance or the lower performance, as in when will it perform best and what will be the worst case, and then try to find the repeatability. By repeatability, how well can I detect those features again if the image is undergoing those changes. And in the second phase, so when we talk about big data, the feature detectors had always assumed that the data will either be symmetrically distributed or will have Gaussian distribution. But since we don't even have a controlled environment anymore, we don't know what will be the distribution, so we decided to use a variant of McNamara test where we actually didn't have any assumption about the distribution of the data, and then we tried to match the performance like between two feature detector and see which one is better. So the proposed data set actually had 539 unique scenes, and then the resolution was 717 in cross 1080. So these were the three image transformation which we made. The inspiration for the three of them was, if we try to capture a scene, same scene by two different people, it can be like the camera settings change, so obviously the compression ratio will definitely change, and when we are trying to upload it on the internet as well, so the compression techniques apply, and sometimes we don't even have a clue. So we applied JPG compression, and there was compression variation from 0 to 98% with around 14 discrete steps. At the same time, we decided to develop some blur changes and change in illumination. So all of them were around 10 to 14 discrete steps. So since this, we were publishing this in a remote sensing journal, so we decided to even take an existing data set, which was the state-of-the-art data set in remote sensing, where we had 100 images, satellite images taken up. And so we selected around 11 feature detectors. As I had mentioned previously, I would like to reiterate, this can be, we can change the 11, we can select any number of them and we can change them again. So what we found out was, so MSER was supposed to be the best performer when it comes to feature detector in the literature at that time. But then when you apply JPG compression, we saw that the moment the JPG compression reached to 20%, the performance of MSER decreased. If you can see, it just significantly decreased. Whereas if you look at the other performers, the best performance was by SIF, where we could actually achieve around 95%. So which was very much contradicting the literature present at that time. We had done more analysis, which I'm not presenting over here, but if anyone is interested, we had done not only, there was in-depth analysis done. So I will just like to conclude by saying that the main idea of this research was to make this framework available from people from all walks of life. And at the same time, we wanted to make it robust and flexible so that we can use for evaluation of features of big data. It also actually, we also wanted to see the in-depth analysis of selecting any technique before actually applying them. And then this can actually be implemented in the other works of computer vision or big data analysis. I think that's it. Thank you so much.
Hi everyone, my name is Abhijit Sengupta. I'm from Essex Business School, and I'm going to present about this. And when I created the slides, it's only then I realized that the title is too long. So I'll just make it a bit short, and I'll say that I'm going to use computational methodologies to make a computer choose something as mundane as orange juice. Okay, it's a big change from sophisticated algorithms which are looking at things like vision and recognition, etc. But it's as you will see, there is a lot of sophistication involved because of the complexity of the markets that we are dealing with here. So I'm going to talk about is consumer behavior and computational methodologies, but in particular use of agent-based methodologies in building models of consumer behavior. So just as an acknowledgement, in this project I was working with Dr. Glavin from Unilever, and the data was provided by Unilever, so acknowledgements to them. as usual. So what are the aims and of this particular, what were the aims of this particular project? So as you can imagine, it was to build models of behavior, in particular agent-based models of behavior of consumers in particular markets, okay? And from the methodological perspective, the whole idea was to build a validation methodology appropriate for the kind of complex models that we are building, the kind of heterogeneity that we are building into the model, which was otherwise quite difficult. So we hope that we would be able to contribute methodologically in at least trying to come up with some sound validation methodologies which would help us to build some robust models. And then using these methodologies to do some predictive analytics. And we will also briefly talk about the potential application domains that we were aiming for in this project. So why did we choose consumer packaged goods? Of course, the sponsors of the project were at that time Unilever, so for them that's the main area of concern. However, if you look at the properties of consumer packaged goods industry, the particular aspects that come out of the data is that, first of all, they're extremely heterogeneous, noisy, and there is a lot of intervention within the data, within the market. So what do I mean by intervention? The retailers, manufacturers are constantly changing things like prices, advertising, and other kinds of marketing inputs into the arena. So it's a high intervention area, resulting in a lot of heterogeneity and a noisy, volatile market. So given this kind of a noisy, feature-rich market, how can we use different kinds of computational methodologies to capture some of the volatility in the market, okay? And one of the things that we did not specifically include here, but what we wanted to do was create a methodological platform which would enable us to also incorporate things like nonlinearities such as feedback loops, word of mouth, networks, social networks, etc. Okay? Although I'll qualify this talk by saying that in this talk at least we have not included any such effects explicitly. Okay, so as a brief background, in marketing, in the area of marketing, people generally use, of course, statistical methods are being used, and the kind of methods that are still prevalent heavily are discrete choice models, because this is about choice of particular products. So discrete choice models, as well as time series models, which, because the data that you get is generally over a time series. The focus of these models were generally short-term analytics and short-term predictive predictions, so that any particular kind of intervention could be modeled immediately to give an expected output. But what these models suffer from is generally extremely poor out-of-sample predictive ability. Okay? And also they do not have the flexibility that computational models will give you in terms of either playing around with different nonlinearities or making some counterfactual assumptions in the data which will help you to do some completely disruptive analytics. And that's one of the things that we'll talk about here as well. So how do we contribute? We develop the multi-agent simulation. We also develop the validation methodology. And in the model, we include, which is extremely difficult using traditional methods, we include not just the more economically driven utility-based approaches, but also in the modeling, we incorporate psychology-based approaches, which gives it a behavioral element or behavioral flavor. In particular, we are looking to sort of try and model the bounded rationality of consumers, at least from one or two different perspectives, if not others. And what it does give us is a rich predictive ability at both the macro level, which is at the market level, as well as at the micro level, in our case, which would be the household level. Any of you from Switzerland? No? Any of you familiar with this market or this particular brand, Le Shop? Okay, if you're not, then let me just qualify by saying that Le Shop is a Swiss brand who specialized in online marketing, consumer packaged goods markets, but their specialty was that they would, like what Tesco's and Sainsbury's do nowadays, they would deliver at home. And these were the first guys to start home delivery through online channels in Europe. And they started it in 1997 when the internet itself was quite at its infancy. So that's their specialty, and they grew tremendously over the period. So the data that we get is from Le Shop. However, it is not from that old, from 97 onwards. The data that we use is much more contemporary. We use, as you'll see, we use data from 2007 to 2009 to build and calibrate these models. And this is the data covers almost all of Switzerland, but only with a few of its provinces and zip codes excluded. And the category, as I said, is fruit juices. We concentrate only on one particular category right now. There is potential to develop models which can handle cross-category purchases as well, using the same methodologies. So this is just a snapshot of the kind of noisy volatility you see in consumer packaged goods markets, in particular in Le Shop. If you look at even bigger markets than Le Shop, the amount of volatility is just going to go up. So there are brands, for example, here we are looking at the movement of brands which, and this is 1 year's worth of data, weekly data, brands which move up and down all the time. Some move together, some move against each other. It's a complete mess if you just look at the top line picture. This is what we look at, because it's fruit juice, we look at data from the flavors as well, and we see a very similar picture in qualitative terms. So the model that we built is based on 3 basic assumptions. Of course, it's a modeling exercise, so there will be some assumptions. The first assumption that we make is that at least consumers are able to rank their alternatives. So they look at which alternatives they are considering at any point in time, and they are able to rank them consistently. Now, we build the ranking itself through the modeling, but at least we are saying that there is an element of ranking made by consumers of the different choices available. All products and product characteristics remain unchanged during a given time. So that's another assumption that we make. For the data that we have, we cannot allow during the calibration or initialization of the data of our model for new products to jump in or tastes and preferences of consumers to vary radically, and that's a simplification. However, our counterfactual analysis that you will see does introduce a completely brand new product to see what might have happened if such products were available in the market. In any case, let's just move on. Okay. So as I said, the consumer choice that we have is based on two steps. One is the typical economics-based utility framework, where we define utility in a certain way, and the second is what we call strategy-based framework, which is where the bounded rationality, etc., start creeping in. I'm not going to. I'm sorry. The maths has been. It's a bit out of place. Probably it's a version issue, but anyway, I wouldn't have gone into the maths deeply because of lack of time. What I'm going to do is just briefly explain what the mathematical underpinnings of the model were. So what we did was we said that each product, we developed what we call a product space, which was composed of dimensions representing different attributes of a product. So because it's fruit juice, so we looked at things like the brand, we looked at flavor, and we looked at pack size. And what we said was each product could be placed at a particular location given its characteristics within that product space. However, that's very obvious, but what we went further and what we said that given consumers' purchase history, we could place consumers within that attribute space as well through various, I'll show you how, but what we did was we also placed consumers in that space. And next we use a very simple distance function to say if a consumer is given a certain product, given the ideal location he would like to be in based on his past purchases, the disutility is given by the distance. Okay, so in our utility function or disutility function, we build in 2 elements. We build in this distance, normalized distance, and we also build in the price element. So the utility is based only on the characteristics of the product versus what the consumer might want, and with with and along with price. Okay. In terms of the other side of the consumer choice model, which is the bounded rationality bit, we built what we call strategies. And there were 2 complementary strategies. One we call loyalty, and the other one we call change of pace. Loyalty is nothing but the tendency of an individual household to keep on buying the same kind of products that they have purchased before, whereas change of pace is the fact that it's just the opposite of it, or complement of it, where they're trying to change over and move out of their set pattern and try and do something different. So both these elements were brought in and based on a certain what we call memory length. So we allowed these consumer agents to have certain memory lengths, that is they would remember not their whole entire purchase history, but let's say the last 4 or 8 instances they went to the shop actually. okay, which is again based on our survey of the literature where we saw that memory lengths are bounded, and again, these were the two lengths we played around with. So we build, for agents, we build the memory functions, and based on these loyalty and change of pace strategies, we built what we call a consideration set. I'm not going to go into the details, but basically what it means is that each consumer with a certain probability will either choose the loyalty strategy at any given shopping instance, or he would choose the change of pace strategy. Based on which one he chooses, his consideration set is different. His loyalty will, if he chooses the loyalty strategy, he will be choosing something from his previous purchases, whereas if it's a change of pace, he will be trying to move into something different. And strategies are applied independently across dimensions and not on the product as a whole. Obviously we define a probability of choice for each consumer. Now this is the kind of algorithm that the consumer agent in the simulation goes through. It looks at the product available, goes through the psychology-based choice to decide on which strategy to choose. Based on that, has a consideration set, and from that consideration set, chooses that one which sort of maximizes or is the highest in his ranking order. Okay. The data itself comes from 3 years, and we use 3 different years of the data to do 3 different activities. The first one is we calibrate each product and each household in terms of their product space and also their position in the product space. The second set of weeks or the second year is used to calibrate their choice between in the utility function, which is omega, which determines the weight given to the price versus the product attributes. And finally, we use the last one to develop some prediction measures or tests to see how well this works. So this is basically how we put consumers in the attribute space. So if you have 3 products, one was bought 5 times, the other one was bought 2 times, and this one was 1 time in that brand and flavor space, the average of these 3 is what we are saying is what the consumer would ideally like. There is no way to say that this is what the actual household ideal point is, but this is just an estimation of an ideal point roughly, which works pretty well as we'll see in the results. And then we also find out what the alpha or the probability of choosing one of the strategies is. I won't go through the validation methodology, it's quite a lot. Since there's only 6.5 minutes left, I'm going to straight to what we call the results, the macro and the micro results. So the validation basically built up a model for each and every household. For every household, we built their initialization set, which is the ideal point. We built the weightage that they give to attributes and the price. And finally, we also built the choice between which strategy they choose, loyalty versus change of pace. And we did it individually for each and every household to build up a whole collection of parameterized households. Okay, so this basically shows you our predicted and actual sales for brands or for a few brands out there. Okay, so what we have here is the green one. The red one is the actual one. The blue and the black ones give you the 2 different memory lengths that we used, and the green says no strategy at all, where they just go for a utility-based choice without any bounded rationality. And as you can see, and if you read the paper, you'll see that the memory 4 generally works the best in most of the cases, except for those kind of groups that we built whose past history is quite sparse. So if you have any reasonable amount of past history, you will have a very good idea of what their choice is going to be, at least of the brands and flavors. Now this is what we call macro level calibration, because what we are doing is we are trying to see which product each individual household buys and which product. At this point, we're not looking at which attributes they buy individually. And since we are trying to match the product choices, we can sum them up and create the market shares. So this is what we call macro level calibration. Then comes micro level calibration. Again, I'm not going to go to the table, but this is what we try and do is for each individual household, we try to see how many of the different attributes were we able to match for every week, for every purchase that they made. So out of the 3 attributes that we used, brand, flavor, and pack size, we try and see, are we able to at least match 1, at least 2, at least 3, or none at all. Okay, sorry, 3 or none at all. So that's the kind of measures we try and take to see how much of the predictions are available, can we make. Just as a top line figure, for brands, we were able to match around average 52 to 63%, 52% of the time as a mean across households. If you take the different groupings altogether, it will be slightly different as well. As you will see, the rate of prediction for a purely random model, which is the blue circle, is much lower. So there is something happening in the model which is far better than a random model. And in fact, it is also far better than just using the utility-based framework and going for, it's much better to use a memory-based framework using bounded rationality strategies rather than just going for a purely utilitarian one. This is just a histogram of the parameters that we finally estimated. Again, no point. But the most interesting bit starts here, where we are able to do what we call a bit of counterfactual analysis. This grid shows here, in the data that we had, if you look at the brands on the x-axis and flavors on the, brands on the vertical axis and flavors on the x-axis, the blacks show you where currently products lie, whereas the white spaces are empty spaces. That means there is no product in terms of brand and flavor which currently occupies that particular slot. So there is a lot of white space available for manufacturers to play around with. And that's what the most interesting thing about this methodology is. It allows you to do that. I haven't seen anything else out there which will actually, at a very minute household level, will allow you to do this. So what we do is we go for introducing a hypothetical brand which does not exist, or hypothetical product which does not exist. The brand that we choose is gold, one of them which was quite prevalent in the data, and the product that the flavor that we choose is apple. And we try to see for different levels of prices and pack sizes what would be the predicted market shares for each of these different combinations. If you can do this kind of a scenario analysis, then at least it gives some toolkit to managers who can now play around with this and choose particular white spaces in order to introduce new variants in the product space, which will give them a good idea of whether it would be viable or not. I'm not saying this is 100% obviously will work, but at least now we have something out there based on the kind of individual level models that we have built, which will allow you to do this kind of a counterfactual analysis. And we see that a small low-priced gold branded apple juice will actually do pretty well in the market versus any other combination. So finally, some applications of this kind of framework, things like complementary predictive capability, which gives you some additional leverage on how to predict markets, noisy markets. Solution space for automated algorithms. Because automated algorithms work, can use these as the starting point to build further developed models. You could, as I just showed you, you could actually use these models to build to do some disruptive analysis. That is, try and introduce a new product variant which doesn't work, which hasn't existed before, introduce new technologies, introduce radical shifts in product preferences, etc. And of course, you can build simulation toolkits, which we at that time were being built in Unilever as well. So these are the references built over the last. The talk is based on these 3 papers which we published over the last few years, and I'm happy to distribute these copies if you want, and I look forward to hearing your questions as well. And I'm right on time. Thank you.
Hello, good morning. Claudia Martinez from Reform. We are a policy think tank conducting research across different areas. I'm particularly interested in the privacy and security aspects of big data. And I was wondering, what were your thoughts on the use of distributed ledgers or blockchain technologies to ensure the integrity of data when sharing data, basically? Thank you.
I'm not familiar with the topic, but my understanding is that it's not sustainable because it uses blockchain technology, relies on the consumption of electricity, and so it's not really something we want to encourage, because eventually we'll have to consume so much energy, and to generate that energy will generate pollution. It's not a way really to go forward. Maybe in the short period of time it could be workable, but in the long term I don't think it is really an avenue we should pursue.
Can I pick up this question, because I was at a presentation very recently, though we have not done work within the center ourselves. So blockchain technology basically relies on whoever is in the network validating the same transaction. So if you have 1 million people, 1 million nodes in the network, every node needs to validate the transaction. So if you have a lot of these nodes, there will be a point where there's going to be a bottleneck. But I'm aware of work that has started developing in a completely different way. So instead of having everyone validating every single transaction on the network, there are now methods that rely on a subset of the nodes, essentially validating transactions. So this bottleneck can be alleviated. And I'm happy to give you some references, because there is a non-profit foundation that is working in this kind of technology. Other questions?
Hi, I'm Richard Potter, and if you could take me as a generic person speaking on behalf of local government, I was thinking in particular on the following things for social media, and a little bit in terms of the pictures of potential relevance and use for emergency planning. That, you know, if an event, a fire or a flood has happened, whether, you know, looking at social media helps you record where these things are happening, and maybe some of them it can be through, you know, help through the use of pictures to see where the fire is, where the flood is, how big it is, things like that.
Well, in our case, was considering certain major event, and then look for tweets that are related to that major event. Then, depending on frequency of terms, we define the support, which is at the threshold value. So if the frequency of terms occurring together exceeds that support, then this is retrieved. Then we use the frequent pattern mining algorithm to find the frequent patterns. So depending on frequency, whenever there is a peak in frequency, then there is something is happening. And this is how we detect our events.
So you could potentially use these sort of methods, and they have been actually proving quite effective in disaster situations like Haiti, I think. So in a lot of these cases, you have news being reported, and that's why we're working in these methods through social media rather than the news headlines, because there's always this delay. You're putting an article together. So it is possible with this kind of frequency sort of algorithms to detect events and then do scenario planning, disaster management. Are you aware of any work, Abhijit, that works in this space of disaster management using multi-agent systems and agent-based modeling? Because that's another link into this work.
Yes, there is currently a lot of work on using these kind of multi-agent simulations to work on disaster planning. It could be flood related, it could be fire related, it could be disease related. So epidemiology, that's where it started actually. Epidemiological studies is where agent-based modeling in social science started, but it's a big area, and we could talk about references later on.
Other questions?
Hello, I'm Karina Grosson. I'm from Brunel University working on machine learning. My question is for Professor Klaus McDonald. You showed in your data unsupervised learning because you're doing clustering and the normalization using the mean. How would you do normalization when you use supervised learning, or what would be the best way, like in classification, regression? Would you use different for training and testing, or the same, or for the whole data set first?
Okay, thank you for the question. I'll try to answer this one. So when you talk in terms of computer vision, when you talk about supervised learning, for instance, I said 3 R's, right? So when you say recognition, in that case, you have to have supervised learning, where you need to show your model. For instance, now we have deep learning. You need to show your neural network or feature detector that this is cat. Like there are a few pictures which show them that this is cat, and then when later on they will get test images so they can identify cat in a different circumstances. So that will be supervised learning. But we do have unsupervised learning techniques as well. For instance, in case of tracking, where you need to track an object, but you don't need to know which object it is. Like, there is no learning power involved at that point. So over there we have unsupervised learning techniques also, but when the one I was showing, we had a supervised learning technique where we were dividing the data set into 70 to 30 part. So the 70% was for the training and the 30% was for the testing. I hope I've answered your question. Thank you.
There was another question at the back.
Thank you. Hi, I'm Abdellah from the Luxembourg Institute of Socioeconomic Research. I'm dealing with public policy evaluation. Anyway, I'm interested in the method that Professor Salhi presented before on data privacy issue about the distant metrics that you introduced in the presentation. And I was wondering how you deal with the elaboration of all the variables that you are considering in the analysis. Basically, is it that you are standardizing or maybe normalizing all the variables in the data set so that you cannot basically really know whether they are, for example, gender or cities or age, whatever else characteristics, so that we are not capable to link this information to any individual characteristics. So we are just dealing with deviation, standard deviation. I don't know.
Yeah. That's a good question actually. The power of this methodology or this approach is that it looks at the problem, and the problem is clustering. Clustering is above any specific area. So you could do clustering in the medical area, or in, as we have seen just here, in the retail sector, or you cluster anything. And that's just something we have to do, put things in groups. And so why this methodology is very powerful is because it transcends the data itself and the context. It goes right to the level of the problem, and then it says, aha, I'm clustering, therefore I am in the NPcomplete class, I can look at another problem, and I can choose. I chose TSP because it's already done. I could choose any problem. There are thousands of them from that tree, or from that graph. And when you transform the data, as we said, the good thing about clustering, transform it into a TSP, because it's natural to think of clustering as similar. You put things similar, and in terms of distance, it makes sense. You say that two cities which are close, the distance is short, match, if you like, two objects which are similar. If you try to turn your clustering into some other NP-complete problem, it's still, the maths say it's doable. Mathematically, we can prove that it's doable. There is a transformation. However, it may be very tedious. It will still be done in polynomial time, but polynomial, it depends on the degree. If the degree is very high, it will still be costly. So not all these transformations are as good as each other. However, they exist. So the data, when you transform it, you don't, as I have shown, you go from data which is on this criteria, scores of these countries on the Copenhagen criteria, and then you turn them into a distance matrix. And you do it. There are a way of doing that. Of course, I didn't show the whole thing, and it's cheap to do. And the context has changed. And why it is important to change the context is because the context gives away a lot. If you tell people, you say, this is medical data, immediately you attract insurers. Those who, for instance, sell life insurance, they want to know, if any of their customers has health problems, and then they hike their premiums. And so if you don't show the context, the context is as important as the data. Of course, the data they will give them the particular patient, but the thing that will attract them initially is the context. Is medical data, let me look. If you tell them, actually this is a logistics problem, they will not be interested. The insurance will not be attracted. So that is the beauty of it, and all the transformations are watertight. They're done. The transforms are mathematical. There are papers there, and you can follow all the literature, and it's all done. Okay.
Thank you, Abdellah. I just realized that though we don't have Elena here, I'm aware that a colleague of yours is available for questions. Yeah, okay, so he's no longer available. No, Elena left, that's the colleague.
I can answer.
Yes, so do you mind, so I'm so sorry, I should have spotted that earlier. So if we have any questions for Elena's paper, that was the first piece of work that we heard about around understanding hip replacement patterns and the different types of cups, I believe. We have someone who can answer questions. So have we got any questions on this piece of work or any of the other papers?
Yeah, I have a question on the...
You have a question?
Yeah, I have
okay.
a question, if I can ask a question. So in the talk there was a slide talking about the Weibull distribution, and you wanted to estimate the parameters. There is parameter k. So what is k in that?
Okay, it is a shape parameter.
What is it?
Shape parameter for Weibull distribution.
Okay, so is it what is it? Is it an integer, or I thought it's not the number of the...
No.
Okay, so it's a continuous. It is a continuous variable.
Yes,
okay.
Yes, positive continuous variable.
Okay, fair enough.
Any other questions?
Just following up on the question about the privacy issue, and a little bit inspired by the lady who asked about blockchain, and I think kind of one of the issues there might be that because it's distributed, if somebody works out the inverse of the transformation, then everybody who has the distributed copy can potentially invert it and get back to the original data. So I understand the kind of removal of the context as being a key advantage, but what's the what additional advantages there say of going from clustering to TSP over clustering, but we conceal all of the names of the variables. So we've got hospital data, but instead of male and female, we switch it to apple juice and orange juice, and kind of instead of age, we change it to price per litre or something like that, and kind of conceal the data in that way.
Yeah, you can conceal it. Sorry, you can conceal the data that way, but I'm talking from the mathematical point of view. This approach is not fail-safe. Someone who is really intent on finding what is the data about, and the context is known, and then they will find out. So I'm talking from the mathematical point of view. The most sophisticated, the safest methodologies, mathematically based, are what I say the homomorphic encryption approaches, and these ones do not work for large data sets. And so you cannot do any sophisticated data analytics because complex algebra is not involved, is not supported, and so you will not be able to do regression. You will not be, do variation analytics, for instance. So that's the limitations of that. So you could scramble. People do that all the time, but it's not really very I would say usable today for very large data sets. What we are putting across or forward is mathematically sound. What I have said is all mathematically watertight. These transformations are mathematically watertight. The NP-completeness class is very well studied. It's known. It's not. This is 70s really technology, even though complexity theory continues. It's a big field in theoretical computer science. And one of the biggest problems is this P is P equal to NP. This is still one of the biggest problems in modern mathematics and computer science. So you have got a lot of problems. The context change and the data. So the data, if you like, changes in implicitly or indirectly. And so it's I think this is the safest way. The issue that no one has picked up. Maybe if I leave it open, maybe someone will pick it up. The issue is that I said that you pick a problem. So I have picked up clustering because I know clustering and I know that clustering is NP-hard and I can do that. But data analytics is not just clustering. There are other things. I think I can do data mining. Data mining is also part of that. Other parts of machine learning can be done, but there are other problems which are easy but still difficult in terms of, because we are dealing with big data, with large data sets. These problems are not in the NP-complete thing, so I will not be able to, so there is a limitation there. However, what I'm quite confident about is that most of the data analytics problems are NP-hard. And therefore, you know, so we have got this class from which we can find P dash. So our problem is finding P dash. T is always there is one, but if you want to transform to another problem which has not been linked before to other problems except one, then you have to invest some time to find transformation T.
We've got a question here.
It's a quick question. In your you have come up with your mathematical solutions, but yeah, and my question is about computation, the location of the computation, because you derived your equations based on the assumption that it will be a solution for privacy and security. So in your case, if there is a company who will deliver a computational task and there is a user and who has got the data and requires some analytics from this company, so are you, your solution is saying that the computation will still be done by company, or you saying that you will shift the problem to the user and the computation will be on the user's computer? So I'm thinking about the computer systems. Where do you plan to do this computation?
The computation can be done anywhere, because the computation can only be done if you have got the data. So you have to get the data. We are trying to protect the data. So as long as the data is protected, I can give you the data. You can have it computed on the cloud, on the cloud computer system. You can have it given to your neighbor, anyone, because the data is completely concealed. What is important, what you could say, is now we are asking a different specialist, because initially we have a problem which is that of a data analyst. We want to do clustering, so a statistician is involved. Here, when I turn it into a TSP, I'm actually involving an operational research guy. Okay, so I give it to an operational research guy because it's an optimization problem, to find out the minimum, the shortest tour, and then from there, when I get it, I will then extract the clusters.
So it would involve a user to have trust to another third party still and give the data, which would create a replication.
You can't trust anybody, because it's that I give you the distance matrix. It's a logistics problem. It's no longer a clustering problem. It's no longer medical data. That's it. Once you transform it into a TSP, it's a distance matrix, and you don't see anything about the origins or the original context, and so it's completely safe.
In an ideal scenario, where would you plan to do this computation to have the best privacy and security scenario?
I will look where it's cheapest. That's the ideal thing. I'm an optimization guy, so I have this big computation to do, to this TSP, which is expensive to solve. I will give it to someone who can do it for me in a cost-effective way. That's what I would do. If I can do it myself, of course, there's no problem. If I can't, I will pass it to the cheapest, the contractor.
Why are you looking at me? I'm not
well, and of course,
Any other questions? We have another one at the back.
Sorry, I wanted to make the second one, but I didn't have the time before. Actually, linked to the first question, let's say that I'm interested, again, to you, to Professor on data privacy issue. If I have to deal with treatment effects, evaluation of treatment effects in terms of impact analysis, okay?
Yeah.
I can be really interested in heterogeneous treatment effects. So clustering, of course, is when we have to deal with big data. Clustering helps statistician and also can provide policymaker. We can provide policymaker with conclusion, let's say, or preliminary results on potential treatment effects, looking at the effect of, I don't know, of different treatments, might be a training program, might be a medical treatment, and so on. The point is that if I'm using these distance metrics, how can I profile? If I want to make profiling, I mean, you know what I mean?
Yes, I know what you mean. It's just you. I'm sorry to say, but you just have not got the idea yet.
Okay.
The data, mathematically speaking, P and P dash are equivalent. They are in the NP class. Okay, they are both equivalent. I will give you a good example, just to tell you what it is. Suppose you have cars which come out of an assembly line. You actually have cars coming out. Now you need to paint them. You don't just go and say, I'm painting this white, this one red. This you do a market research and you find out that actually people prefer red cars. So you want to paint more cars red and maybe less yellow, maybe very few yellow, quite a lot black, and so on and so forth. The way you sequence them, because of the way you have to change the guns, the beaks of the guns, the paint, etc., that takes time. It's a sequencing problem. This is equivalent to the TSP. I can actually turn this one into a TSP. So you will tell me, how can you go from painting cars to finding the shortest route? Yes, but mathematically you can do it. And it's all done. This is done in the 70s. It's all that, okay? The technology is there and robust. So same thing, you cannot profile, you can do anything once the data is transformed. You only solve the problem you have. I solve the TSP now. I'm thinking of finding the minimum, the shortest tour for this guy. But once I have got that, I will then apply my T-1, because I know T, I know the transformation. So when I say in my slide, I just kind of in a superficial way said, objects are cities, the similarity are distances, and the objective is this. You have to do a little bit of work there. It's not all kind of free. But the work is not as hard as the original. It still can be done in polynomial time, because these transformations mathematically again are proven to be computable in polynomial time. Otherwise there is no point. So it's quite cheap to transform. Once it's transformed, you cannot do profiling of what you have been thinking of initially. It's a completely different context, and there is nothing you can do. However, when you go back, you get your results. You can then go back to your data. You can do it. You say, these are my clusters. Let's look at the original data set and let me see if I can, interpret them. Do they make sense, etc. But that is done now in your office, at the source of the data, not at the level of the guy who is providing the expertise to solve the TSP. So it's all safe.
So if I understand right, Abdel, what you do is essentially you take one problem, mathematically formulate it into the travel salesman problem. So you do the transformation from one to another, which means you don't need to have perhaps the access to the data in the original.
No, in the original, you have to have the data later on, because otherwise
you have to have the data later on. So by transforming one problem into another, then you do the work in the travel salesman problem essentially. And then you take the result and then you transform it back. You can go from one to another, which is quite an interesting concept, because from a mathematics point of view, we know how to do this.
It's done. It's all in the literature. There's nothing. I have not invented anything. My contribution is just to say, this class can be used to promote privacy, to help with privacy. That's the only originality. Everything else is old hat, is known, is safe. There is a literature, a vast literature on all of that.
Obviously, the presentations have provoked a lot of questions, and I'm sure there will be further discussions. But I think we are now due to have lunch, so you can all join me to thank our speakers one more time.